Welcome to my talk. I'm Matthias. I work as a cryptography engineer at Web3 Auth. We do distributed key management for blockchain users, basically. And this is joint work with Hart Montgomery from the Hyperledger Foundation. So what is this talk about in one slide? As I said, at Web3 Auth, we run a distributed key management service where we basically make it easy for users to have their keys managed by us, but in a decentralized way. We don't learn the keys, and this is based on secret sharing. I will tell you a bit more about how it works. We run this service now since, I think, 3 to 5 years roughly, and we manage about 20 million keys in the databases. And this poses some scalability concerns or questions. So we try to improve the scalability of the service. We thought about ways of doing this. And one way we came up with is, what if we had an efficient distributed key derivation mechanism that we can use? And we will see that this could potentially reduce the server load by quite a bit and the key material that we need to manage. And we found that we can instantiate such a scheme based on a PRF construction that was proposed in 2013 by Bonnet et al. And this is based on learning with rounding, and it turns out that this construction is very nice for evaluating it efficiently in MPC. So a bit more into detail. Basically, the task of distributed key management is offloading the task of key management to a set of servers where none of the servers should learn the key. The key is typically shared between the servers using Shami secret sharing or something like that. And the user should be able to access the key at any time. The traditional approach of setting something like this up is at the start, when the user registers, you run a distributed key generation protocol where the servers engage in a multi-party protocol. And at the end of the protocol, a user identifier is assigned with a private key that is secret shared among the servers. So none of the servers learns the key, but the user can now access his private key by authenticating against the servers, or potentially also running some multi-party signing protocol after that. So now each of the server has to store a secret key share for each of the users. So we can easily see that this grows linear, so the amount of key shares that we have to maintain is linear in the number of users. And also think about settings or scenarios where you want to refresh the key shares. So you have to do that millions of times, potentially run refresh protocols, or if you want to migrate to a new server infrastructure, you have to migrate quite a bit of key material. So one way that you can improve upon this is using a distributed key derivation protocol. So the idea is that you have a fixed master secret key, just as a normal key derivation function, but now this master secret key, KS, is shared among the servers. The user identifier U is a public input to this key derivation function. And in the distributed protocol, the servers derive the user secret key KU. Again, the output is secret shared. And what we get is that we can basically derive the user key shares on demand. So when a user registers with our system or requests his key shares, we can derive the key shares on demand. The servers only need to store shares of the single constant size master secret key. So now the key shares database size is constant. It's independent of the number of users. And also like refreshing the key shares of the master key is just a simple, a much more efficient protocol. Of course, now the question is, it would be nice to have this distributed key derivation protocol, but can we actually realize it efficiently and with all the properties we need for this specific application? So what are the properties that we need? One good thing is that the inputs to this, so I call it distributed PRF here because it's basically a PRF that we are using for realizing this. The input is public. It's the user identifiers. They're not secret. This makes a few things easier. the output should be secret shared, and the output distribution must be that of the key distribution of the target cryptographic scheme, like a signature scheme. It should be robust to faulty servers, so if we have some malicious servers among the server set, we should be able to tolerate that up to a certain threshold. We want standard cryptographic assumptions because this should actually run in production eventually. We want low round complexity so that we support servers that are not within the same data center but have some latency amongst each other. And we want it to be composable with other protocols like an MPC signing protocol so that we can use these key shares of the users and run a signing protocol on top of that. So how did we, basically the core contribution is showing that we can create a distributed signing protocol, a distributed key derivation protocol from this PRF that was proposed in 2013. And this is based on learning with rounding. I don't want to go into the details, but the nice property of this PRF is that it has a lot of linear pairs that are very efficient to evaluate, and then it has this modulo Q operation and the round P operation. These are the nonlinear pairs, and these will be a bit more tricky to evaluate efficiently in MPC. I said this. Yeah, so let's see what we can do to actually make this concretely efficient. So basically, we did a few optimization steps to make this work. The first one is very simple. Basically, this matrix product that you see in the middle is for mapping the input X, the public input X, which would be the user identifier, to a random matrix. And we can replace this by a simple call to a hash function because the input is public, so we can just let every server compute this, this hash function result. The next thing is a matrix vector multiplication by the secret key. Now, since the matrix is public, this is just a local linear computation. If we take the parameters P and Q as powers of 2, it is not so hard to see that the modulo Q and the round P operation become bit truncation operations. So first you truncate the higher order bits, and then you truncate some of the lower order bits. And we will see that this will enable a very efficient implementation in MPC. And last but not least, we need to map the result of this original PRF, which is a vector of log 2 p-bit elements, so between a vector where each of the elements is between 0 and p minus 1. And we need to map it to the range of the target cryptographic scheme, so the key range of the scheme. And we do this via a simple, basically, accumulation step in the end. And turns out that basically most of the stuff, as I said, is basically non-interactive in MPC. The only tricky part is the non-linear part where we do the bit truncation, but there are known protocols for that. We even didn't, for this work, we didn't have to optimize. We have some further work where we even optimize this further. But so the standard result that you get is you run, this bit truncation runs in 2 plus log Q over P plus log Q rounds. And this concretely turns out to be 8 rounds in practice. I will show you some concrete numbers in a bit. So to actually know how concretely efficient that is, we did a prototype implementation so far using the MPC framework. You can look it up, it's open source. For our evaluation, we use the maliciously secure Shamir protocol as a base layer protocol in MPC. Basically, that is what our code gets compiled to. We run it with 3 parties, but any parties would be possible, and we require an honest majority. So two parties must be honest in our case, in our setting that we evaluate for. Yeah, the target key distribution is a 256-bit prime field, like an ECDSA key, you could think. The lattice parameters that we use, we have 2 parameter sets. One optimizes for round complexity, the other optimizes a bit more for communication complexity. And we fixed the lattice dimension to 512, which should give you a security level of about 128 bits, which we basically We didn't do the analysis of this ourselves. We took it from an existing paper that evaluated the parameters in this setting. So yeah, here are some benchmark results to get a feeling of how it compares to previous work. So there were other works that were designing PRFs that run efficiently in MPC or FHE or in a CQ proof system. So basically these PRFs are designed that they can be efficiently run in arithmetic, expressed as an arithmetic circuit. As we optimize for rounds, ours has a significantly, like by an order of magnitude, lower round complexity. So as I said, we can run in 8 rounds. So in terms of latency, this is far superior if you compare it to the other protocols and like extrapolate what that would give you in terms of network latency. If we estimate 100 milliseconds of latency between each of the servers, then you would get a significant difference between what our protocol gives you and what the existing protocols give. Also, our protocol is relatively efficient in terms of computation, so it's very simple computations that you have to do. The downside is we need more communication, and this also is like one of the open questions, I would say. Like, we need a lot of pre-shared random bits for basically this is some pre-processing step that you see here in the total communication column. And it would be interesting to see if we can like kind of generate this pre-shared random to make this pre-processing more communication efficient. And we have some ideas, but not implemented yet. And as I hinted before, there's one work of ours which builds upon that, where we optimize the bit truncation protocol a bit more. So actually we now can run this in 5 rounds respectively. And there is a related work which builds something similar based on exponent VRFs. And this basically makes the trade-off. It uses a more involved cryptographic primitives, exponent VRFs, but achieves actually a very similar result in just 1 round, but uses a lot more computation. And turns out that we can build an exponent VRF also from this PRF construction that we presented here. And this is also something that is shown in the works that are outlined below. And with that, thanks for your attention.